More than 4 billion tons of cement are produced worldwide each year to build our cities,
bridges, dams, and nearly all of modern civilization. But to create this seemingly simple gray material,
humans have had to tear through massive mountains, quarry hundreds of thousands of tons of rock, and push them through. Is one of the most brutal industrial processes on Earth. From explosions that shake entire mountainsides and crushers weighing dozens of tons, to kilns
hotter than volcanic lava, it all serves a single purpose: turning rock into cement. Are you curious about how this complex process works?
But to understand why manufacturing cement is so complex, we first need to understand what this material actually is. More than 2,000 years ago, the ancient Romans discovered that mixing volcanic ash with lime created an ultra-hard material, allowing structures like the Colosseum to stand strong for millennia. Since then, cement has become the undisputed king of construction materials. On the surface, cement looks like nothing more than an ordinary, harmless gray powder. But in reality, it's a complex chemical compound. Its core ingredient must be limestone, which is rich in calcium carbonate, precisely blended with clay containing silica and aluminum oxide. Through the melting and structural transformation process, cement gains a truly unique characteristic: the ability to hydrate. Unlike typical adhesives that dry out by losing water, cement actually thirsts for water. It requires water to trigger chemical bonds, creating a highly durable interlocking crystalline network. This gives it massive compressive strength, waterproof capabilities. However, cement has a fatal Achilles heel. It is extremely brittle and has terrible tensile strength. That is why in construction, builders must always combine it with rigid steel frames to create reinforced concrete. The first step in cement production is limestone mining, as limestone accounts for more than 80% of the raw materials used to make cement.
At the Cardinal Aggregates open pit quarry in Ohio, USA, more than 700,000 tons of limestone are extracted each year
to reach the limestone deposits beneath the surface.
Workers must first remove the overburden owning giant excavators and specialized haul trucks. This material is not discarded. Instead, it is stockpiled for resale or used in environmental restoration and land reclamation projects. On average, for every 10-foot section of overburden removed, approximately 1,600 tons of limestone are exposed beneath the surface. Next, the blasting process begins. Dozens of drill holes are bored deep into the quarry face, with each hole reaching a depth of approximately 30 feet. High-powered drilling rigs penetrate the rock at speeds of nearly 5 feet per minute,
creating a precisely planned network of holes across the entire blasting area. Once drilling is complete, the holes are loaded with explosives.
The delicate yet powerful work of connecting the charges. Each yellow cord is meticulously routed to the centralized system, allowing engineers to trigger the blast from a safe location. After all safety checks have been completed, the engineer presses the button. In just a few seconds, a single blast can break loose between 15,000 and 25,000 tons of limestone, providing an enormous supply of raw material for the production process that follows. Once the blast is complete, giant hydraulic excavators move in to collect the broken limestone. Their massive buckets, each capable of holding several tons of rock in a single scoop, load the material directly into heavy-duty haul trucks waiting nearby. These quarry trucks are among the largest vehicles on the site. Some of these gigantic machines can cost hundreds of thousands. They haul freshly blasted rock from the quarry face to the primary crusher, ensuring a steady flow of raw material for the cement production process. The raw limestone is then transported by giant haul trucks to the primary crushing and sorting area, rather than being sent directly to the cement plant.
This is because many of the blasted rocks are still extremely large, with some boulders measuring several feet across and weighing several tons,
making them too large to enter the production line. At the crushing station, the limestone is fed into a massive jaw crusher. Using tremendous compressive force, the machine breaks down these huge rocks into pieces measuring roughly 10 inches or less. Reducing the size at this early stage makes the material much easier to handle and transport on conveyor systems. After primary crushing, the material that meets the required size specification is sent directly onto conveyor belts, while oversized rocks are automatically routed back to the crusher
for further processing. After being crushed to the appropriate size, typically less than 4 inches,
the limestone pieces are then transported onto a massive conveyor system. This material continuously moves along a conveyor belt over 1 kilometer long,
spanning the distance between the quarry and the plant before being dumped into a storage area where tens of thousands of tons of material await homogenization before entering the clinker transformation process. Alongside limestone, clay is transported into massive dome-shaped much storage facilities. Inside these structures, stacking and reclaiming machines operate continuously in carefully programmed cycles. Layer after layer of material is deposited in a specific pattern, creating large stockpiles with a stratified structure. This layering process plays a crucial role in homogenizing the chemical composition of the raw materials, helping reduce the natural variations that exist between different batches extracted from various locations within the quarry. After homogenization, the raw materials are carefully proportioned before entering the grinding system. In most cement plants, the mixture typically consists of about 75% limestone, 20% clay, and small amounts of corrective materials. Depending on the plant's design, the blend is fed into either a 2-chamber ball mill or a vertical roller mill, massive industrial machines capable of processing hundreds of tons of material every hour. Inside the mill, the limestone, clay, and additives are
with most particles measuring less than 90 microns in size.
The result is a uniform material known as raw meal, which serves as the primary feedstock for clinker production. Some older facilities
still use the wet process, where the raw materials are mixed with water to form a slurry before grinding.
While this method can make it easier to control the chemical composition of the mix, it requires significantly more energy and has gradually been replaced by the more efficient dry process technology used in most modern cement plants. The raw meal is then fed into the preheater tower, a multi-story structure composed of several cyclones stacked on top of one another. Inside the tower, the raw meal gradually travels downward,
while hot gases from the rotary kiln below flow upward in the opposite direction. This counter-current heat exchange system
gradually raises the temperature of the material to approximately 850 degrees Celsius before it enters the main kiln. In the calciner section, located near the base of the tower, most of the limestone in the mixture begins to decompose into calcium oxide and carbon dioxide. This pre-calcination process removes a large portion of the carbon dioxide before the material reaches the kiln.
Leaving the calciner, the raw meal enters the rotary kiln, where temperatures can exceed 2,700 degrees Fahrenheit.
Inside this massive steel cylinder, which is installed at a slight angle and rotates continuously, the material undergoes partial melting and recrystallization, gradually forming small nodules known as clinker. Clinker is the key ingredient that gives cement its characteristic strength and binding properties. A modern rotary kiln can stretch more than 300 feet in length and produce anywhere from 3,000 to over 10,000 tons of clinker per day. The intense heat required for this process is generated by finely ground coal, natural gas, or alternative fuels, creating a powerful flame inside the kiln. Although the kiln itself is hundreds of feet long, the material typically takes only about 30 minutes to travel from one end to the other and complete its transformation into clinker. However, this stage is also responsible for the majority of carbon dioxide emissions associated with cement production. Large amounts of CO2 are released both from the fuel used to heat the kiln and from the chemical decomposition of limestone that occurs during the clinker-making process.
After cooling, the clinker is transported to the cement grinding stage.
Here, it is blended with gypsum and, depending on the type of cement being produced, additional materials, such as ground, granulated blast furnace slag, or fly ash may also be added. The mixture is then fed into high-capacity grinding mills, where the clinker is continuously crushed and ground by steel balls or high-pressure rollers until it becomes an extremely fine powder. The finished cement typically achieves a blane fineness of approximately 3,000 to 4,500 square centimeters per gram. In general,
the finer the cement, the faster the hydration reaction occurs. directly influencing the rate at which concrete develops strength.
Dimensions, including fineness, mineral composition, and expected compressive strength. This ensures that every batch of cement consists.
After production, cement samples are tested for fineness, composition, and strength. The data obtained is compared against technical standards to ensure
that each batch of cement has consistent and uniform quality.
After completing all quality control inspections, the finished cement is transferred from storage silos to the automated packaging system. Here,
high-speed bagging machines accurately dispense the required amount of cement into each bag, typically 50 kilograms, before the bags are
automatically sealed. In modern facilities, these systems are capable of packaging thousands of bags every hour. Once they leave the bagging machines, the cement bags travel along a conveyor system for additional inspection. Automated sensors verify the weight of each bag and detect any packaging defects, removing non-compliant bags before they can proceed further down the line. The approved bags are then transported to a fully automated palletizing area. There, industrial robots or specialized stacking systems arrange the bags into multiple layers, according to a carefully designed pattern that maximizes stability during storage and transportation. When the pallet has been fully loaded, it passes through a stretch wrapping machine. The plastic film secures the bags into a single unit, while protecting them from moisture and dust during handling and shipment. A typical pallet contains between 40 and 60 bags of cement. Finally, the completed pallets are moved to storage warehouses or loaded directly onto trucks, railcars, or ships for distribution to building material suppliers, concrete batching plants, and construction sites across the country. From here, the cement begins its final journey to the concrete mixing plants. There, it is combined with familiar ingredients such as sand, crushed stone, and water under the control of automated metering and mixing systems. In just a few minutes, this seemingly simple gray powder transforms into concrete,
the foundational material for houses, bridges, dams, and virtually every modern construction project in the world. The journey of cement was interesting, wasn't it? Thank you for watching until the end, and goodbye, and see you in the next video.